If you've worked in a modern organization, you've likely endured the standard corporate training seminar, a 2-hour mega course, or a relentless half-day workshop. Cognitive science has a term for this approach. It's called mass practice. The brain physically struggles to absorb continuous, massive data dumps. When you cram a high volume of information into a single session, the preceding and succeeding concepts interfere with one another. Memory becomes fatigued, and the data simply jumbles together. A common industry response involves fragmenting long-form videos into smaller segments to match perceived attention spans. This system utilizes a specific instructional architecture engineered to manipulate the mechanics of human memory. Engineering this system requires 3 evidence-based mechanisms: spaced scheduling, active testing, and strict duration boundaries. Shifting from mass practice to this engineered architecture provides a scientifically backed path to transition a workforce from passive viewing into actual, measurable behavioral change. In the late 1870s and into 1885, Hermann Ebbinghaus rigorously experimented on himself to study human memory and the concept of forgetting. He identified a severe biological constraint that dictates all learning design. Human memory decays at a predictable, rapid rate over time. This chart shows Ebbinghaus's forgetting curve. Notice the sharp initial drop-off. Without intervention, a learner loses roughly 67% of consumed material within 24 hours. However, Ebbinghaus tested himself using nonsense syllables. When data has real meaning, the curve looks quite different. Mapping new information to existing, relevant context slows down the decay rate. A series of acronyms related to your specific job won't fade as quickly as random syllables. However, the biological reality of inevitable memory loss remains intact. Because biological decay is a constant, instructional design cannot rely on a single exposure event. It requires a system engineered to actively disrupt the forgetting process. This deliberate disruption is known as the spacing effect, or spaced retrieval. Distributing learning over time combats learner fatigue. It prevents information from mixing, eliminating the cognitive interference of mass practice. An intentional re-exposure event physically resets the retention curve. For scheduling, the uniform approach sets mathematically equal time between events. Alternatively, the expanding schedule progressively widens the intervals, say day 1, day 3, then day 7. Current research from cognitive scientists suggests expanding schedules are structurally superior for mitigating rapid forgetting. Optimal learning design doesn't repeat information randomly. It strategically times re-exposure to strike at the exact moment a memory trace is about to fade. Spacing out content only solves the timing equation. How a learner interacts with that content during those intervals dictates the strength of the memory. Researchers Henry Roediger and Jeffrey Karpicke studied the testing effect, proving that the act of recalling information physically modifies and strengthens the memory trace. Compare passive review activities like rereading a manual or watching a video with the active retrieval required in self-testing or quizzing. The underlying cognitive mechanism here is that the very act of using our memories alters our memories. The physical act of recalling information modifies the memory trace. It makes the correct information more accessible while simultaneously weakening competing incorrect information associated with the same cues. True microlearning mandates active testing. You aren't quizzing the learner to grade them for HR compliance. Instead, you are forcing them to retrieve the information to physically fortify the neural pathway against future decay. What is the optimal length of time for these spaced, active micromodules? In 1985, researcher Ralph Burns rigorously examined the relationship between presentation duration and idea recall in chemistry students. This graph illustrates his findings. Maximum recall is concentrated in the first 5 minutes, where students retain about 35% of ideas. Retention stays steady for 10 minutes, but recall impact plummets to its absolute lowest level after the 15-minute threshold. Modern data corroborates this. Assistant Professor Philip Guo conducted a massive analysis of 6.9 million human-computer interaction sessions on the edX platform. Guo found that learner engagement drops precipitously for any video asset exceeding 6 minutes in length. The data highlights the extreme inefficiency of longer formats. Viewers of 12-minute videos average only 3 minutes of total watch time, abandoning nearly 75% of the content. Exceeding the 5 to 6 minute threshold directly triggers cognitive fatigue. Traditional, longer formats are objectively counterproductive to the primary goal of retention. By combining the variables deduced from Ebbinghaus, Bjork, Burns, and Guo, we can build a unified first principles model for microlearning. The final architectural blueprint is clear. Instructional designers must deploy 5-minute modules mapped on an expanding timeline that force active recall. To see how this theoretical framework results in the actual application of skills in clinical practice, we can observe its implementation in high-stakes environments. A continuing medical education study tracked physicians who attended a face-to-face clinical course. One group received post-instruction spaced retrieval, facing active quizzing at 8 and 16 days. The control group received 0 follow-up until week 18. When surveyed at week 18, the group utilizing the engineered microlearning protocol reported significantly greater, measurable changes in their global clinical behaviors. Microlearning is a specific tool. It should not universally replace all deep dive organizational training, where complex initial context needs to be established. However, when the objective is long-term retention and modified behavior, adopting an engineered microlearning architecture is the most scientifically sound investment an organization can make. It aligns corporate strategy directly with the hard limits of human biology.